So this is just a continuation of the notes that we were doing before. We started off just being introduced to scientific notation, how to write it. We continued with that on Tuesday, and then we got up to comparing scientific notation, which we did in the journal. What I want us to be able to do today is multiply. So multiplying and dividing scientific notation. Okay. So I'm really just going to do some sample problems, do a couple sample problems, and I'm going to give you a couple practice problems. And with the remaining time today, I would like to try to finish those packets that we were working on. Yep. So we've already learned about Avogadro's number. So Avogadro's number is 6.022, or just 6.02 is fine, times 10 to the 23rd. That's the actual number, right? And that represents how many particles are in this unit called the mole. And we further clarified that particles could be atoms or molecules, which I like to abbreviate as MCS, depending on the substance that we're dealing with. If we're dealing with an element, then we're talking about atoms. If we're dealing with a compound, then we're talking about molecules. So what I want you guys to be able to do, our success criteria is performing calculations involving scientific notation. It's all about scientific notation, and today we really want to focus on these calculations. Is if we know how many particles are in a mole, I want you to be able to tell me how many particles are in 2 moles, or 5 moles, or 10 moles, or 3.6 moles, or 15.1 moles. These are all just random numbers I'm throwing out there. But when we're dealing with substances, we're not always going to deal with just 1 mole. All right? So I want to know, like, if you have a fraction of a mole, if you have 6.35 moles, how many particles does that represent? So let's start real basic, all right? If we know how many particles are in 1 mole, what if I said to you, how many particles are in 2 moles? What would you do? You would multiply by what? By 2, okay? So if we know there's 6.02 times 10 to the 23rd, and I'm just going to put RP. This stands for representative particles, which means atoms or molecules. Depends on the substance we're talking about. So there are 6.02 times 10 to the 23rd representative particles in 1 mole, which I could say, make it like a ratio. 6.02 times 10 to the 23rd representative particles per 1 mole. How many are in 2 moles? Which you just said, let's multiply by 2. So how do we do this? Okay, well, 2 is not in scientific notation. It's just a normal number, right? 2. So all we have to do, real simple, is take the normal number and multiply by the normal part. So I would take 6.02 times 2. So it's 12.04. But we're not done because 6.02 times 10 to the 23rd is a huge number, right? So what I do now is after I multiply the normal parts of the two numbers, I just put that times 10 to the 23rd on the end. And then I have still RPs, representative particles. Pretty easy, right? Now, if you had this as your answer, I would say, cool, great job. You get your points, you get your credit. But here's the problem. Scientific notation, that front number is always between 1 and 10. 12 does not fit between 1 and 10. So what I can do is I can adjust this number to make the front number between 1 and 10. I can take this decimal point and move it one spot to the left, which would make my new number 1.204. But now here's the thing. If I do that, 1.204 times 10 to the 23rd is not the same number as 12.04 times 10 to the 23rd. So what happens is if you have to adjust this number at the end, if I have to move that decimal place to make it 1 less, I have to compensate by making the exponent 1 more. So instead of 23, it would be 24. So those are actually the same numbers. Now, like I said, if you put this, like on a written portion, you left it like 12.04 times 10 to the 23rd for my quiz, I'd give you points. Because realistically, the idea with this is being able to figure out the number of particles in a certain number of moles. It's not necessarily being an expert on scientific notation, but you do need to know how to use scientific notation. Now, where the problem comes is what if it's not a written out thing? What if it's a multiple choice test, like your final exam? You need to be able to look at this and recognize, hey, that would be the same thing as this because this might be the possible choice listed, which it would be because we'd put the answer in the correct scientific notation. Okay? So let's try another one. Yeah, get used to it because we're going to be put RP for now, but we'll have to focus on using atoms and molecules later. Which one are we talking about? So this time I'm going to say, what if we had, instead of 1 mole, we had 4.7 moles. Okay? We have 4.7 moles. How many RPs are in that? So what would you do now? We're still going to use this fact, right? We know this. We know there's 6.02 times 10 to the 23rd representative particles per 1 mole, right? So how are we going to find out how many particles are in 4.7 moles? Times that by 4.7, exactly. So I'm going to take that, and I'm going to multiply by 4.7 moles. So now I'm going to need my calculator. Again, I'm going to take this 4.7, which is a normal number, and I'm going to multiply that by the normal part of the scientific notation, which is the front part, right? The normal front part. So I'm going to go 4.7 times 6.02, and I get 28.294. I'm going to round it off to 28.3. And then don't forget, so this is another mistake people make. They do that regular multiplication. I'm done. Not yet. We multiplied by scientific notation, so we got to add the times 10 part onto it. And in this case, it's times 10 to the 23rd. So your answer is 28.3 times 10 to the 23rd representative particles. Or you might see it written as 2.83 times 10 to the 24th. Either way, what? Yes. Yep. I just want you to be able to recognize this in the case of we have multiple choice, and the answer is listed as that. 6.02 times 10 to the 23rd is always the amount of 1 mole. Yep. All right, so I want to give you 2 practices to try. Or maybe we'll just do one. We'll do one. Practice number 1, and we'll just do 1 practice for multiplying. So in this case, I want to say that there are 3.1 moles. All right. And I want you to tell me how many, this time I'm not going to use RPs, I'm going to use the real deal. How many molecules would that mean? All right, so I'm going to go ahead and pause the video here and give you guys a few minutes to try this. So 3.1 moles, how many molecules would that be? All right, so let's go ahead and check answers. So again, we have 3.1 moles. We know there are 6.02 times 10 to the 23rd particles in 1 mole. In this case, we're talking about molecules. So how many are in 3.1 moles? We got to multiply. So if I take 6.02 and I multiply by 3.1, I get 18.662, which I'll round off to 18.7. And then times 10 to the 23rd molecules. All right. And if I wanted to change that to the real deal scientific notation, it would be 1.87 times 10 to the 24th. You do not have to have it rounded the same as me. No, this is just the same. This is just how I would do it. But if you had 18.662, 18.66, 18.7, rounding off to 19 is a little too much rounding, but I'd like it to at least be to 1 decimal place when you round it off. Okay, so that's our answer. That's what we do. Show you one more thing with multiplying, just so you know. But what if we had to multiply 2 numbers that are in scientific notation? And I'm just going to use basic numbers. I'm not even going to worry about Avogadro's number right now. But let's say we had like 2.0 times 10 to the 15th. And we wanted to multiply that number by 3.0 times 10 to the 4th. So these are both really big numbers. If I wrote them out with all the zeros, I guess the second one's not that bad, but the first one, that would be a lot of zeros after that. It'd be a lot of work, it'd be a mess. So with scientific notation, it actually is going to make it really easy to multiply big numbers, or even divide, which we'll see next. But if I were to multiply these two numbers in scientific notation, it's the same idea. Take your normal part and multiply it normally. So 2.0 times 3.0. What is 2 times 3? 6. So I'm going to write 6.0. But now what I'm going to do with it being scientific notation is I got to have that times 10 thing. Okay, so 6.0 times 10. And then when we multiply scientific notation, what we do with those exponents is we add them. Okay, so add the exponents. 15 plus 4 in this scenario, which would be 19. I just make that my new exponent, and there's my answer. Now, the reason why I didn't stress that earlier is because realistically for what we're doing, you're not going to be multiplying scientific notation. But I wanted to show you that because when we get to dividing, you are going to be dividing numbers in scientific notation. For example, like if I said, hey, instead of having 6.02 times 10 to the 23rd particles, what if you had 1.8 times 10 to the 25th? I don't know, just made that up. So if we are doing this type of problem, we are going to have to divide scientific notation. Okay, so dividing scientific notation. So I think I said just now, I said, what if instead of 6.02 times 10 to the 23rd, we had 1.8 times 10 to the 25th? Let's say atoms this time. Okay. So if I have 1.8 times 10 to the 25th atoms, I said, hey, how many moles is that? So for all these problems, whether we're multiplying or dividing, we are basing everything off the simple concept of Avogadro's number. We're always talking about 6.02 times 10 to the 23rd representative particles, atoms or molecules, depending on what we're dealing with. And we know that's how many are in a mole. Okay? So if we know that's how many are in 1 mole, then what I want to do to find moles here is I'm actually going to divide. I call this thing, a lot of people call this thing, a conversion factor. And we're starting to get into something called dimensional analysis. So this is how dimensional analysis works. Just to start, just basic dimensional analysis. What you do is you look at the question, okay? You take what's given to you in the problem, and you're going to start your problem with that. So whatever's given to you in the question, I call that the start. The reason why is I'm going to start my equation with that. 1.8 times 10 to the 25th atoms. And a lot of these equations are going to have a top portion and a bottom portion. So what I always like to do at the start is always put it over 1. and then I write times. So always write what's given to you as the start. You're going to start your equation with that, just put it over 1 and write times. Now what we're going to do is we're going to use our conversion factor. So what I can do is I can either use 6.02 times 10 to the 23rd atoms per 1 mole, or I can flip that upside down, whichever is needed. How do we know which one's needed? Well, when we do dimensional analysis, it's all about units. So whatever units I start with, I want those units to be on the bottom of my conversion factor. Because really what we're trying to do in dimensional analysis is cancel out the units we start with to get new units that we're looking for. In this case, we're starting with atoms, and we want to convert that to moles. So in this scenario, if my conversion factor normally has atoms on top, but I know I want to have atoms on the bottom, I'm going to flip it upside down. So instead of 6.02 being on top, I'm going to put 6.02 times 10 to the 23rd on the bottom. And I'm going to take the 1 mole, instead of being on the bottom, that's going to be on the top. So what happens is, if I've got atoms on the top part of the equation and the bottom part of the equation, then the units atoms, just the units, not the numbers, but the units of atoms cancel out. And the only ones I'm left with now are moles on top. I know this is confusing right now, and it's going to be confusing for a little while, but if you keep paying attention and working with me, it'll be really easy within the next week, I promise. All right? So atoms are canceled out. So now at this point, all we do is we're going to multiply across the top to get a top answer, and then we're going to multiply across the bottom to get a bottom answer. Now the top is really easy. I have 1.8 times 10 to the 25th, and I'm multiplying that by 1. Well, that's just 1.8 times 10 to the 25th. But I do have a unit up there, moles. The next step is multiply across the bottom, which again is really easy. It's just 1 times Avogadro's number, 6.02 times 10 to the 23rd. And there are no units left on the bottom because the only ones that were there were atoms, and we canceled those out. So you can see how this becomes a division problem. So when we divide, similar to when we multiplied, just take your normal parts and do the normal thing. So my normal front part is 1.8. My normal front part on the bottom is 6.02. I'm just going to divide them normally. So I'm going to take 1.8, divide by 6.02, and I get 0.299. All right. So I just divided the front part normally. Next step is you're still going to have to write times 10. So when we multiplied, we added the exponents. When you're dividing, you subtract the exponents. So I'm going to take this top one, 25, and I'm going to subtract the bottom one, 23. Anybody know what 25 minus 23 is? 2. And that's my exponent in the answer. All right. And the units are still there. So the answer would be 0.299 times 10 to the second moles. I could switch that up, move the decimal 1 spot over to the right. But if I make the decimal 1 spot greater, then I got to compensate by making the exponent 1 less. So you could see it as that. Could even see it as 29.9 moles. Let's not worry about that right now. But that's dividing. So we will continue to work on this Monday. Bring your packets Monday. Run out of time again. All right, but we're done with notes for a little while. That's good.